In this video, we're going to discuss the Arrhenius equation. So previously we discussed how the energy of activation was related to the rate. That is, you had a larger energy of activation, it was a bigger hurdle for your particles to overcome, and so that inhibited the ability for your reaction to proceed. You needed higher temperatures so your particles were moving faster on average, so that more of them had the needed energy to overcome that barrier. Well, this was studied, and Arrhenius devised an equation that said that the K, the rate constant, was equal to A e to the negative activation energy RT. Activation energy is E of A, R is the gas law constant, T is your Kelvin temp, and A is the frequency factor. A represents the number of collisions that appropriately interact with each other to be able to perform the reaction. So how many collisions are there, say, in a given second, and what proportion of them are going to be at the correct angle for the reaction to occur? Different reactions, different molecules interacting may be a little bit more likely or a little bit less likely for those particular reactions to happen. And so A is basically a multiplying fraction that adjusts how many of the molecules that have the necessary energy will actually be able to perform the reaction. Well, this on its own is nice and handy and fun values to calculate. However, how we go about finding this information usually is to go and do rate calculations. So we're going to have an example here. We're going to have two runs, and we're going to have some starting concentrations at the initial time and at, say, 60 seconds. In both cases, we're going to start with half-molar material, and they react fairly quickly. And so run 1 is going to be 25 degrees Celsius, run 2 is going to be 45 degrees Celsius. Well, in the colder run, what we find is that it goes down to 0.35 after that minute. But at the hotter run, it goes down to 0.23. More of it has been consumed. More of whatever this reaction is, A go into B, just to make our life simple. Some molecule is breaking down. Well, we have our rate laws. In this case, if we know that the reaction is first order, we can say that my rate is equal to K times the concentration of A to the first. So if we've done that work and already determined that it is, say, a first order reaction, we can take the integrated rate law to find K. We can say that the natural log of the concentration initial, so 0.5, we'll do run 1 first, over 0.35 must be equal to the KT. Natural log of your starting concentration divided by your concentration at time is equal to K times the time. Well, we know that our time was 60 seconds. So I can divide time over, take your natural log of those values, divide by 60. What we'll find is that K1, K at 25 degrees Celsius, is going to come out at 0.00595. And if we did that for run 2, use the same equation. We'd say, oh yeah, natural log 0.5 starting, but we went down to 0.23 at our hotter temp. That's going to be equal to K2 times the 60 seconds. We can divide by 60 seconds down. I'll have a larger number when I do this division because the bottom was smaller this time. And so larger than the value divided by 60 is just going to come out a little bit bigger. And indeed, we find that it's 0.0129. And these would be per second. We can find K values at two different temps. Well, I can compare things. Rearranging this equation a little bit, we can derive one that's fairly familiar. You may remember it from Clausius-Capron equation. Similar style, that the natural log of K2 over K1 is going to be equal to the negative activation energy over R 1 over T2 minus 1 over T1. Hey, this kind of looks like delta H of vaporization, pressure 2 over pressure 1. It's a similar idea. We're relating two physical properties through the energy barrier between them at different temps. We can derive the same equation out of the Arrhenius relation, which means if I know two rate constants from different temperatures, I can solve the energy of activation. Or if I know the energy of activation, I can solve rate laws at different temperatures. In this case, since we had data that gave us the K values at two different temps, I can plug those in. Natural log of 0.0129 over 0.00595 should equal negative activation energy over 8.314 joules per mole Kelvin times 1 over, well, temp 2 was 45, so 318.15 Kelvin, and temp 1 was 25, so 298.15 Kelvin. Run that, rearrange, get rid of the negative, our activation energy comes out at 30,514 joules per mole. Because the rate is related to the activation energy, and how many of our particles will have that amount of energy is related to the temp, if I know rate constants and temps, I can find how big that hurdle is. Differently sized hurdles will allow a different proportion of molecules over for the same temp increase, and so we can determine just how big that hurdle was. So while the Arrhenius equation was written out as the individual one, often really we're going to use this relation between two of them in order to find out more info. Because now that I have the activation energy, that also lets me go back up here and solve A. I can plug that activation energy in. Let's pick run 2. My K was 0.0129. That's going to equal A e to the negative 30,514 joules per mole divided by, and this is all in the exponent, 8.314 joules per mole Kelvin times the temp for that run, which was 318.15 Kelvin. Divide all this to the other side so you can solve for A. And what we'll find when we calculate this out is 1320.18, and our K would have been in per second, so this is still per second. It's a frequency. And so we can find an A value for this reaction as well. The Arrhenius equation allows us to relate the rate constant to the activation energy and the temperature in a way that we can take actual data we see from the concentration changes, use our integrated rate laws in order to find some K values, plug those in to find the activation energy. And so activation energy itself isn't directly measurable. When it came to things like enthalpy of reactions, calorimetry allowed us to actually calculate out the amount of heat released by watching how much heat was absorbed by some other material. However, with our activation energies, this isn't really possible. Our starting material in our product, we go up in energy to reach it, but we go back down as we then proceed the product. The rise in energy here, it's canceled by the same fall there. What energy went in is given back. This is hidden. It isn't given away or absorbed by the surrounding material. It's only the change below here, the delta H of the reaction, that is given off or absorbed by the surroundings and that can be easily measured. So to find these activation energies, we actually have to go through the Arrhenius equation. We have to look at the change in rates with the change in temperature in order to be able to calculate it out. This is also a big part of why some reactions just take forever. When we go and do a reaction that seems to be very, very slow, we'll find that it usually has a very large activation energy. Even if the delta H may be large or small for that reaction, the slower the reaction, in general, the larger the activation energy as a result. But doing these calculations is the only way we can identify it.